Have you ever driven past a highway construction site and found yourself staring at that one machine, the one with the long blade underneath, leaving behind a strip of dirt so perfectly smooth it looks like a pool table? It is mesmerizing to watch, but if you look closer, there's something strange going on. Have you ever noticed that the front tires aren't just turning left or right? They're actually leaning over, like the machine is about to collapse. Why on earth would a 40-ton machine need to tilt its wheels? Is it broken? Is the axle snapped? Or is there a method to the madness? Well, don't worry. By the end of this video, you are not only going to understand the physics behind that wheel lean, but we are also going to tear this machine apart, digitally speaking. We are going to look at the powertrain, the impressive crabbing maneuvers, and the secret internal mechanisms that allow this beast to shape the world we drive on. Stick around, because the engineering inside the circle drive alone is going to blow your mind. Let's start where the power begins, the powertrain. This is the journey raw energy takes from the combustion chamber down to the rubber meeting the road. It all starts at the rear. Almost all modern motor graders, whether it's a Cat, a John Deere, or a Komatsu, run a massive 6-cylinder inline turbo diesel. We place the engine in the back for two very specific reasons. First, it keeps the heat and noise behind the operator. Second, and more importantly, that heavy engine acts as a natural counterweight for the incredible force being applied by the blade up front. It's simple physics. You need weight in the back to keep the drive wheels planted when you're pushing tons of earth. But raw horsepower is useless without control. That energy flows from the engine into the transmission. Now, unlike a standard hydrostatic loader that uses fluid to drive, graders usually use what's called a countershaft transmission. Why countershaft? Because inside that casing, you have multiple steel shafts running parallel to each other, loaded with heavy-duty gears.
Why chains? Why not gears? Chains are incredibly durable. They handle shock loads better, and they allow the distance needed to space the wheels out for stability. These chains run in a partial oil bath, constantly splashing lubrication onto the links and sprockets. If you ever need to service them, mechanics look for a master link through an access port, but these systems are designed to last thousands of hours without failure. All right, let's answer the question everyone asks: the front axle. Unlike a car, the steering here is hydraulic. Two cylinders push and pull the wheel hubs to turn them left or right. A tie rod connects them to keep the geometry perfect. But what about the lean? Technically, we call this wheel lean. Imagine the grader is pushing a heavy load of dirt with the blade angled to the left. Physics dictates that for every action, there is a reaction. As the blade pushes the dirt left, the dirt pushes the entire front of the machine to the right. This is called side draft. If the wheels stood straight up, the machine would slide sideways, ruining the grade. By leaning the tires into the cut, leaning them against the force, the operator counteracts that slide. It digs the tread sidewall into the ground, acting like a cleat. It keeps the machine driving straight even when moving tons of earth sideways. It is not just a cool trick, it is essential physics. Moving back toward the cab, we find the articulation joint. The grader is actually two frames pinned together in the middle. Hydraulic cylinders allow the machine to bend in the center, usually up to 20 or 25 degrees. Why do we bend the machine? First, it creates a tighter turning radius, helping this long beast turn around in tight cul-de-sacs. Second, it allows for crab steering. This is the pro move. The operator can keep the rear drive wheels on the flat, solid road while swinging the front frame and blade out to work on a muddy ditch or a steep slope. This keeps the heavy engine where the traction is while the blade does the risky work. Now for the business end, the drawbar. This is the A-frame structure underneath the front. At the very front of the nose, it connects via a massive ball and socket joint. This ball takes incredible abuse. It pulls the entire weight of the cut. Connected to the drawbar is the circle. This is that giant ring gear you see. It allows the blade to rotate 360 degrees. Underneath, there is a hydraulic motor that spins this ring. But here's a brilliant piece of engineering. The gearing inside is a worm gear driving a helical gear. Why? Because a worm gear is typically non-reversible. If the blade hits a rock, you don't want that force to spin the circle backward and whip the steering controls out of the operator's hands. The worm gear locks it in place. But what if you hit a massive boulder? Something has to give or the steel will snap. That is why we have the slip clutch. It's a mechanical fuse. If the shock load is too high, friction discs inside the drive box slip against each other. It absorbs the impact, saving the transmission, and then grabs hold again. It is a literal lifesaver for the gearbox.
Here is the cool part. You will see these drum-like components called clutch packs. These are essentially stacks of friction discs and steel plates bathed in oil. When the computer calls for a gear, hydraulic pressure clamps these packs together, locking specific gears to the shaft. It is instant and it is robust. A grader transmission is unique because it has a huge range. We are talking 8 forward gears and 6 reverse gears. Why so many? Because grading is precise work. Lower gears give you massive torque for ripping hard-packed clay, while the higher gears allow the machine to travel down the highway at speeds up to 30 miles per hour. This transmission prioritizes speed more than a dozer would, because a grader needs to cover miles of road in a single shift. From the transmission, power hits the differential. This component is encased in a heavy-duty housing to keep out dust, mud, and silica. The differential splits the power to the left and right sides. Crucially, it allows the wheels to spin at different speeds, which is vital when you are turning a machine this long. If the differential locked up 100% of the time, you would tear up the expensive tires and the finished road surface every time you took a corner. From there, power moves to the final drives. These are planetary gear sets located at the hubs. You have a central sun gear spinning 3 planet gears inside a ring. This is the final stage of torque multiplication. We trade high speed for raw, earth-moving twisting force right before we hit the wheels. Now look at the back wheels. You'll notice there is no axle running directly to the center of the wheel hub. Instead, the power goes into the center of this large rectangular box called the tandem housing. If we could X-ray this box, you would see something surprisingly old school. Chains. Heavy-duty double-strand roller chains. The axle spins a sprocket in the center of the tandem, and 2 chains run outward, one to the front drive wheel, one to the rear drive wheel. This gives us a true 4-wheel drive in the rear, creating a 6x4 traction profile.
The blade itself is technically called the moldboard. It is not just a piece of steel, it is a surgical instrument. Cylinders allow it to slide left and right, known as side shift, to reach outside the tires. We can also change the pitch. Pitching the top of the blade back makes the cutting edge aggressive. You use this to cut through hard-packed clay or ice. Pitching it forward is for rolling material. It reduces friction and mixes the dirt, perfect for fluffy finish work. Have you ever seen a grader working on a near vertical bank with the blade almost standing straight up? That is done using the link bar. On the side of the machine, there is a bar with multiple holes. By pulling a pin, usually hydraulically from the cab, the operator can unlock the lifting geometry. They extend the lift cylinder, lock the pin into a different hole, and suddenly the range of motion changes. This allows the blade to reach high up a slope or reach deep into a ditch, all while the machine stays flat. It turns the grader from a road machine into an excavation tool. Climbing into the cab, the difference between old and new is night and day. In the old days, operators were known as piano players because they had to manipulate 10 or 12 mechanical levers simultaneously. It was brutal on the knuckles and shoulders. Today, it is like a fighter jet. Most modern Cat M series or John Deere graders have eliminated the steering wheel entirely. Everything is done with dual joysticks. The left hand controls steering, articulation, and gear selection. The right hand controls the blade lift, circle turn, and side shift. It is intuitive, it reduces fatigue, and with floor-to-ceiling glass, the operator can see the toe and heel of the blade perfectly.
On the back, you'll often see a claw-like device. This is the ripper. It is not a plow. It is designed to penetrate asphalt, frozen ground, or rock-hard haul roads. It fractures the material so the blade can move it on the next pass. When traction is an issue, especially in mud or snow, operators install tire chains. Since the grader is light in the front, traction is usually 100% dependent on those rear tandem wheels. Chains turn those tires into grinding gears that bite into the earth. Of course, things go wrong. Graders have a high center of gravity. We've seen videos of them sliding sideways off roads or rolling over into ditches. But a skilled operator can do magic. If they get stuck in mud, they can actually use the blade and the ripper to lift the entire machine off the ground, essentially walking the machine out of the muck.
And speaking of legends, we can't talk graders without mentioning the king, the Champion 100T. Built in the late 70s, it was the biggest grader ever made. It had a 700 horsepower engine and a 24-foot blade. It was a monster designed for strip mining, but it was too big to transport easily. Today, the industry prefers machines like the Caterpillar 24, massive mining graders used to keep haul roads smooth. In mining, a smooth road means faster trucks and less tire wear, which saves millions of dollars a year. Before we go, look at that rear tandem box one more time as the machine drives over a bump. Notice how the box rocks up and down? That is tandem oscillation. It acts like a walking beam. If the front tire hits a 6-inch rock, the axle only rises 3 inches. It halves the impact of bumps, keeping the blade steady. Without this oscillation, every bump the tires hit would transfer directly to the blade, creating a wavy road. It keeps the cut level even when the ground isn't. The motor grader is arguably the most difficult piece of heavy equipment to master, but it is also the most versatile. It combines the power of a dozer with the precision of a scalpel. So the next time you see those wheels leaning over, you will know it is not broken. It's just physics hard at work. Would you have the patience to learn the controls of a machine this complex? Or do you know an operator who makes it look easy? Let us know in the comments below. If you enjoyed this deep dive into heavy metal engineering, smash that like button and subscribe for more. Thanks for watching, and we'll see you on the next grade.